A very good day to everyone. Today I want to present about embedded system project assignment. So my name is Yugendra Ravi Kumar and from VLN session 2 and my matrix number is B112410352. So my group mate number is Sri Mohandan Mahindran, Yugendran Chandran and Kisirin Sukumaran. We are under lecturer from D. Azamzani bin Muhammad Sani and the second lecturer is D. Zarzmizi bin Hamad Isudin. So this is our project title, Smart Plant Grow Box Cooling System. So we are choose this title for our project assignment embedded system. So this is the introduction. Why a cooling system? First one is the problem. Obstacle lies inside the grow box increase the temperature, which is can stress or even damage the plants. Decrease an unhealthy environment for optimal plant growth. The second one is solution. To address this temperature sensor, in installed to monitor the initial condition. Also, it automatically can adjust the fan speed to cool the grow box when needed and keeping the temperature stable also. So the last one is benefit. The system help optimize plant growth, reduce water usage, and increase energy efficiency, making it a smart and sustainable solution for indoor growing. So this is the three interaction. Why a cooling system? So this is the system objective. First one is develop control. Adjust fan speed based on the three temperature levels. So the fir- the first objective, we can adjust the speed fan level based on the temperature level as we want. We can increase and decrease the fan speed according to the plans. The second one is design smart cooling, automatic fan speed for optimal cooling. So we can adjust the cooling system also automatically adjust the fan cooling system. So the last one is create automated system, maintain temperature without manual control. So we can maintain the temperature, the speed and all without our manual control. It automatically created the temperature for the plants in ecosystem. So that's all for me. Thank you.
Everyone, my name is Kesilan son of Sukumaran. My metric number is B1124103227. Today, I want to explain about the system description on my project. Our project is smart plant grow box cooling system designed to automatically regulate temperature inside an indoor plant environment using a temperature sensor. It also continually monitors the grow box and adjusts the fan speed according to prevent overheat, dry soil, and water loss. Now, there are four fan speed modes power on. Number one is switch 0, which is open switch, and low switch 1 for lesser than 20 degree, and medium switch 2 for 20 degree to 24 degree, and high temperature is switch 3 for upper than 24 degrees Celsius. The current mode is shown through real-time LCD or LED feedback, making the system fully automate the minimum manual intervention. Second,
Hello everyone, my name is Sri Mohandan and I'm Lucky Mahindran and my matrix number is B112410342. This is the schematic diagram of our project. So this schematic design shows the main design of the smart plant grow box cooling system, which is the project that we chose. Using the MC68K microprocessor as a main CPU. So it was created. This whole schematic design is created in a software tool which is called KiCad, which is a software specifically for drawing electronic circuit diagrams. Into the schematic diagram, if we see in detail, the system is basically powered by 12-volt DC source, which is regulated to 5-volt using an LM7805 voltage regulator. So if we see here, an LM 35 temperature sensor monitors the environment with its analog output simulated in software, as no ADC is used here. Other than that, a 16 times 2 LCD also can be said as the 7 segment display. It's connected in 8-bit mode with the data lines linked to the data bus and control lines connected to the address lines, which is A1 and A2, while the RW pin is grounded. So if you see here, 4 push buttons are used, which is switch SW0, SW1, SW2, and SW3. So the switch 0, I mean SW1 represents the power button. The SW1 basically represents the temperature, which is below 20 Celsius. The switch to SW2 is represents the indication of 20, the temperature in the range of 20 to 24 Celsius, which is ours. We choose 21 as our main temperature here as our draft. While switch 3 basically for above 24 Celsius, just to indicate above 24 Celsius, and we choose 30 there. So together with that, 4 LEDs are used here, which is for visual indicators, and the fan is powered directly from the 5-volt line for which is which is to make the connection more compact. And as overall, the schematic provides a basic but more functional microprocessor-based temperature control system with input, output, and also the user interface components. Here's the list of components I would like to explain about. So firstly, we have MC6800, MC68K microprocessor, which is the one of the necessary components that have to be used, which is basically the central processing unit, the CPU that controls the entire system. Then four push button or switch is used, which is to simulate various temperature inputs and the power control. Then along with that, 4 LEDs as well is used here, which is to indicate active switch or system status. Then one 7 segment display or the 16 times 2 LCD, as if we follow the schematic diagram, is used, which is connected in the 8-digit bit, which is for visual output to display system state, display system state and temperature info. Then one set of power supply. If you see here the 7805 ILM 7805 power supply regulator, which is for the VCC and the ground terms, which is for provide as we see generally for to provide power to the logic and display circuitry. Then one set of the memory mapped IO registers, which is important as well for interfacing points for reading inputs and writing outputs. Then one control register, which enables the system operation and IO communication, the input and output communication. Then 4 resistors, which is optional, but it will be used if which is known as a pull-up resistors for the switch stabilization. It will be used if it's implemented in real hardware. In this case, it's just a software based tool. So we didn't include those resistors in the schematic diagram, but it can be implemented if it was if you want to do in hardware. Then connecting wires as much as we needed, which is for logical connections between the components, like such as data, the address control lines, as we see in the schematic diagram as well. Connecting wires are needed as much as possible.
Second, I want to explain about the software flowchart. Now, now the flowchart is this is the flowchart that outline the logic, control logic. Once the system power on, it check the temperature based on the reading. It turns the fan to low, medium, or high speed. The flow is coded in easy 68K using the memory mapped I/O and logical switch state to simulate sensor inputs. The temperature three holes are clearly defined to ensure the plant box always stay with the optimal condition. And this is our flow chart, which is power on, and this is the check temperature, and this is the all of the components we have been done in fan turn to medium temperature, fan turn to high speed, and lastly we need to turn off.
About the full coding explanation. So basically, if you see, this project was coded in Easy68K software using which is basically using the MC68K assembly language to simulate a fan control system for a plant to grow in a box. So let's get into this. So if you see here, this program basically starts by defining all hardware addresses and memory variables, which all this includes the display, switch inputs, control registers, and LEDs. Then it clears the system state and enters the main loop where it continuously checks for switch inputs, then manages state transitions and update the display if the state changes or not. Uh, then the next part, if we see, this part handles the switch logic system. There are four switches, which is one for power and three to simulate, and another three for simulating temperature levels. When the power switch is on, the program checks which temperature switch is pressed. Based on that, it sets the corresponding system state like TEP 18, TEP 21, or TEF 30, and lights up the LEDs. Then, if no switches are pressed, the system stays in SYS on mode. So in the next page, if you see, the state mission, if you see here, the state mission handles automatic transitions. After entering a temperature state like TEP 18, the program waits for a short delay and then switches to the corresponding fan mode, like F on L. So this same pattern applies to the medium and high states as well. It helps to simulate like a real behavior where a fan turns on after detecting a certain temperature. Into the next piece, then in this part, if we see, since there's no actual timer, the delay is simulated using a loop. So this keeps the system in one state for a few seconds before switching, which will make the transitions more smoother and more realistic. Here, if we see, the display only updates when the system state changes. So in this part, it's about the display update logic. So this is done to avoid flickering or unnecessary updates. So if the state has changed, the program calls specific routine to update the 7-segment display with the new status like TEP 18 or F on L mode. So into the last part, if you see in this section, each display routine writes a specific pattern to the 7-segment display. So these patterns represent system states like SYS on TEP 21 or F or ONH. So each character is displayed by writing values to memory locations, which is for representing the display segments.
Firstly, press the Assemble Soft button. If there's no warning or error, then we proceed to press the Execute button.
Before we proceed to run our program, we go to View and enable Hardware, where a 8-segment display and each switches will pop up. This when press switch 0, the system will go 1. Switch 0 plays a role as a power switch. When the temperature is below 20 degrees Celsius and the sensor stands, for instance, 18 degrees Celsius, the display pops out as TEP 18. After 3 seconds, the delay, the fan turns on low and displays F on L. Whenever the temperature sensor sends a moderate temperature from 20 to 24, the output is displayed out while following by F on N, means fan on in normal mode. On the other hand, when the sensor sends a high temperature around 30 degrees Celsius, the display shows as TEF 30. Then the fan goes to maximum speed. When the system is not in use, when turn off the switch 0, the display also shows as off.
Now, at the end, now I want to conclude the whole of the project. To conclude, we successfully developed and simulate this smart cooling system using MC66800 microprocessor. Through this project, we learned through about the digital interfacing memories, mapped outputs, and embedded control logic. In the future, we plan to implement this with an actual sensor and real hardware and possible integrate wireless monitor to remote plant care. And it also the microprocessor interface, digital inputs and memories mapped output. And we'd also gain a lot of knowledge in this project and hope we can do a lot of better things. That's all. Thank you.